As Catherine just said, I'm Janice Strong. This is my husband, Jamie Levine. Probably most of the people know that I'm the author of Mountain Footsteps, the hiking guidebook to the East Kootenay. So I'll start the show. Oh. Jamie took this image of the Orion Nebula with his telescope. We'll begin this presentation by gazing up at the night sky. He and I captured all these photographs in this 3-minute introductory slideshow. We photographed these images over the past few decades, and many of them shot within the past couple of years. Jamie has been a hobby astronomer since he was 13, when he received his first telescope. Today he has a few telescopes, and he loves photographing and researching the night sky. And some recent aurora images were taken with our phones. The main part of the show will be presented by Jamie. There he'll delve into the wonders of the night sky. We hope to wow you with some of the fascinating details of our extraordinary, vast, and complex universe. Some of the images in Jamie's portion of the presentation are from Hubble Space Telescope, James Webb Space Telescope, NASA, that all offer public domain images, for now anyway. Some of the topics he will touch briefly on: how small our sun is compared to the stellar giants, how atomic elements formed, how planets, galaxies might have formed, and many other cool topics. So sit back and enjoy the rest of our 3-minute introduction.
Okay, and then we'll start the next part, if the computer does its thing nicely. Okay, I'd like to begin by giving an overview. Oops, forget how tall I am. So I'd like to begin by giving an overview of the vastness of the universe. Almost every spot you see in this picture is a distant galaxy. And this iconic image was taken by the Hubble Space Telescope in 1995. They pointed the telescope to a very blank area of the sky and exposed the camera for 2 days to get this image. The previous picture represents a tiny area of sky, about the size of that yellow dot inside the red circle. And everywhere they aimed that telescope, the narrow view, the scene was the same: endless galaxies. Now we're going to take a look closer to home and then work our way out. Here is our closest neighbor, of course, photographed from our front yard. To give a sense of scale, if the Earth was this big, this is how far the moon would be. And this is how big the moon would be in relation to the Earth. And here's a comparison of the size of the Earth and the sun. Obviously, the Earth wouldn't be this close to the sun. But at this scale, if the Earth was this big, this is how big the sun is. Continuing on, at this scale, if the sun was this big, I guess I could use my pointer. No, I can't. the Earth would be a tiny speck of dust, and that's how far away it would be from the sun. And the nearest star to our solar system would be about 300 kilometers away at that scale, about as far away as Lake Louise is from us. To illustrate the distribution of stars in our galaxy, imagine shrinking down a star like our sun to about the size of a grain of sand. And in this scenario, the stars would be approximately 10 kilometers apart. This is the renowned Voyager 1 space probe, launched September 5th, 1977. On February 14th, 1990, when it was at a distance of 6 billion kilometers away, the spacecraft turned its camera toward Earth and captured this image, the furthest ever photograph of Earth taken. In this image, the Earth appears as this tiny, solitary, pale blue dot within the vast emptiness of space. And to fully appreciate the vast distances in space, it's necessary to understand the concept of a light year. Light travels at just over 1 billion kilometers per hour, and traveling at that speed, it takes just over 1 second for light to reach the moon, and about 8.5 minutes for light to travel from the sun to Earth. And in 1 year, light travels 9.5 trillion kilometers, and that defines 1 light year. But nothing can travel faster. Light is the universal speed limit. Sorry, science fiction fans, nothing can travel faster than light. It's not possible. The nearest star in the night sky is Proxima Centauri. It's 4.2 light years away. And that means light racing at over 1 billion kilometers per hour takes more than 4 years to reach us. That gives you a sense of the distances. Looking at the stars is like looking through a time machine into the past. The further away a star is, the further back in time we see it. When we see the light from our closest stellar neighbor, Proxima Centauri, at 4 light years away, we're seeing the star as it was 4 years ago, not as it is today. And this small region of space represents just a tiny fraction of the Milky Way, our local neighborhood, spanning about 30 light years. And here's the sun in the center, and that little red circle is where Proxima Centauri is, our closest neighbor at 4 light years away. Ironically, most of the stars closest to us, including Proxima Centauri, are invisible to the naked eye because they're too small and faint. And every red star you see here is a red dwarf, far too dim to be seen without a telescope. From 30 light years, we zoom out to 100,000 light years. Now we see the entire Milky Way galaxy. And here we are, the red circle, the red little dot there. We are in the suburbs at 26,000 light years from the galactic center. So when we look toward the Milky Way center, we see what it looked like 26,000 years ago. And our galaxy is about 100,000 light years across and is home to about 200 billion stars. Now we venture out further to our local group of galaxies. The Milky Way galaxy is in the center. And our nearest spiral neighbor, Andromeda Galaxy, is the furthest away we can see with our naked eyes. It's 2.5 million light years away, so we see it as it appeared over 2 million years ago. Here's a photograph that I took of Andromeda Galaxy from our front yard through a small telescope.
How'd you do that, Jamie?
Wait, you'll see. From a dark sky location, This is the Andromeda Galaxy looks like to our eyes. Can you spot it? It's a fuzzy, tiny spot just right at the center. The previous image I did take, it was about a 4-minute exposure through the telescope, tracked. And here's where Andromeda Galaxy is. So if you know where to look in the night sky, you can find that. And you are seeing something that's 2.5 million light years away and seeing the way it looked over 2 million years ago. Before we venture further out into the cosmos, I'd like to bring your attention to how everything in our universe is in motion in relation to everything else. The Earth is spinning around the Sun at 100,000 kilometers per hour, taking 1 year to complete one orbit. The Sun and planets, our solar system, is whirling at 830 kilometers an hour, 830,000 kilometers an hour around the galactic center. And it takes about 250,000 years to do one revolution around the galaxy. Here's the Milky Way, our local neighboring galaxies, the Andromeda Galaxy and the Triangulum Galaxy. They are on a collision course with our Milky Way. They'll collide with our galaxy in about 4 billion years toward the end of the Sun's life. And collisions are quite common in the universe, where small galaxy clusters bound together by gravity careen toward one another in a cosmic traffic jam, with galaxies merging, stretching, and sometimes passing right through each other, as in this picture from Hubble. Here are some images captured by the Hubble Space Telescope showcasing these amazing collisions. Even though collisions are common, in the vast distances between galaxies, the universe is expanding. So in local situations, galaxies may be merging, but overall, the emptiness of space is expanding, making the distances between the galaxies greater over time. Zooming out further, our local group of galaxies is a small part of the Virgo supercluster. And the Virgo supercluster in the center is a small part of the neighboring superclusters. And each one of these little dots or smudges up there is a supercluster. This view is about 30 billion light years across. And the tiny red dot in the center represents the Virgo supercluster, of which our galaxy is a tiny speck. So, where did all the stuff in the universe come from? As I mentioned earlier, there's overwhelming evidence that our universe is expanding. And by playing the clock backward, we see the way it once was as an extremely small, dense, hot state of pure energy. This moment marked the beginning of the Big Bang, the birth of space, time, and all that exists. As the universe expanded and cooled, energy transformed into particles and eventually forming the simplest atoms, hydrogen and small amounts of helium, the two lightest elements in the periodic table. All the other elements had yet to be formed. In the early universe, these atoms coalesced into vast clouds of gas. Dense regions under the influence of gravity began to pull in more gas, growing larger and more compact over time. These collapsing regions eventually gave rise to the first galaxies, where billions of stars, gas, and dust are bound together by gravity. Some of these galaxies were small and irregular, while others grew into majestic spirals or elliptical shapes through the mergers and collisions over cosmic time. Within these early galaxies, the dense gas clouds collapsed further to form the first stars. As the gas clouds collapse, heat and pressure build up due to the gravitational compression. And when sufficient mass accumulates, heat and pressure ignite nuclear fusion, causing hydrogen atoms to fuse into helium, and this event marks the birth of a star. These images illustrate the relative sizes of the stars. Our sun is depicted by the tiny yellow dot. I can't seem to find my pointer. I found it. It's hiding. There's our sun. And the majority of stars in our galaxy are smaller than our sun. However, some are enormous compared to the size of the sun. And this image illustrates the relative abundance of the stars. As you can see, the majority of stars, about 90%, are smaller than our sun, whereas the sun-like stars comprise about 10% of the total star population. While the massive stars are exceptionally rare, they occur less than 1% of the stellar population. Here, the sun lies at the center of our local 20 light-year neighborhood. And as I mentioned before, most of the stars are too faint to be seen with the naked eye because they're too small and they're red dwarfs. Despite vastly outnumbering the brighter stars, these red dwarfs remain invisible to us without a telescope, as I mentioned earlier. We captured this image during a backpacking trip from a dark sky location. But despite the apparent starry expanse, you're only seeing a tiny fraction of the stars in our galaxy. A star's size and stability hinge on a delicate balance between two opposing forces: the inward pull of gravity, which tries to collapse the star, and the outward pressure of nuclear fusion, which pushes against that collapse. This cosmic tug of war not only determines a star's stability, but its lifespan. The ultimate fate of a star is determined by its mass. The small stars can last for billions or even trillions of years, while the massive stars live fast and furious, burning through their nuclear fuel in just a few million years. So what happens when the stars die? Most stars, as I said before, are small red dwarfs. They end their lives quietly after trillions of years, as small Earth-sized white dwarfs. The larger stars, the ones that are about the size of the sun, live about 10 billion years, and they end their lives a little more dramatically. At nearly 5 billion years old, the sun is a middle-aged star, about 4.5 billion years of hydrogen left of fuel to burn. But when the hydrogen runs out, gravity will compress the sun's core to extreme densities, igniting helium fusion and creating heavier elements like carbon. And during this phase, the sun will expand into a red giant, its outer layers swelling to engulf the inner planets, including the Earth. Once the helium is depleted, the sun will shed its outer layers, forming a spectacular planetary nebula. At its heart, a dense Earth-sized core, a white dwarf, will remain, slowly cooling and dimming over trillions of years. And there's the white dwarf. This is the Ring Nebula, a glimpse into the likely fate of our sun. The faint central star is the white dwarf, the original star's dense core. There. And here's a photograph that I took of the Ring Nebula using my telescope a few years ago. Not quite as impressive as the Hubble, but we were impressed. This was taken by the Hubble. Yet another example of a red giant star that expelled its outer membranes, outer atmosphere into space. In contrast to the smaller stars, the massive ones, those over 10 times the mass of the sun, live fast and die young, and they burn through their nuclear fuel at a breakneck pace, fusing the heavier elements until they reach iron, the endpoint of nuclear fusion. Without the energy to resist gravity, the core collapses catastrophically, triggering a supernova explosion. This violent event scatters the star's elements into space, enriching the cosmos with the building blocks of planets and life. This is the famous Crab Nebula, a supernova remnant in the constellation Taurus. It formed after the star's explosive death in 1054 AD. It was recorded by Chinese astronomers as a star so bright that it was visible during the day for over a month. Here's another stunning example of a supernova remnant captured by the Hubble Space Telescope. And this image was taken from our front yard. Here's Betelgeuse over there. It's a massive red supergiant in the constellation Orion. And with a diameter of nearly 700 times that of the Sun, this celestial behemoth is nearing the end of its brief 10 million year lifespan. Located about 550 light years away, Betelgeuse is the closest star to Earth that could go supernova. This spectacular explosion could happen any time in the next 100,000 years or so. Fortunately, a supernova would need to occur within about 30 light years to pose a threat to life on Earth. So when Betelgeuse does go, we'll be safe. Here's a comparison of the relative size of the Sun and Betelgeuse. For those massive stars that end their lives as spectacular supernova, the fate of their core depends upon their mass. For stars that are 10 to 25 times the Sun's mass, the core collapses into an ultra-dense neutron star, where a teaspoon of matter weighs billions of tons. And for stars even larger, those over 25 times the mass of the Sun, the core collapses further into a black hole, creating an extreme curvature of space-time where gravity is so strong that not even light can escape. These stellar deaths are more than just dramatic explosions. They're cosmic factories. Supernovae forge and scatter many of the universe's heavier elements, such as iron and nickel. But the heaviest elements, gold, platinum, uranium, have even more exotic origins. But before delving into these extraordinary processes, it's necessary to revisit stellar beginnings again. Stars form within the immense gas clouds in star clusters known as stellar nurseries. And here's a familiar star cluster in the winter sky, the Pleiades, also known as the Seven Sisters. It's located about 440 light years away. And the Pleiades is a very young star cluster dominated by hot blue luminous stars less than 100 million years old. As one of the nearest star clusters to Earth, the Pleiades offers a glimpse into the early lives of stars. And here's how the Pleiades appears in the night sky to us. We could see it in the night skies these days in the winter. Over time, star groups like this will disperse, going on their own separate ways. But many of the massive stars remained in gravitationally bound pairs. And when these gravitationally bound pairs live and die together, their core remnants, the neutron stars, may spiral closer together until they collide and merge in a cataclysmic event. And these rare collisions unleash enough energy to forge the heaviest elements, including gold and platinum. Colliding neutron stars occur once every 10,000 to 100,000 years in the Milky Way. But it's amazing to think that the gold we use in jewelry, technology, wedding rings was born from the fiery aftermath of colliding neutron stars. The very atoms in our bodies, carbon, oxygen, iron, are billions of years old, forged in the hearts of stars. We are quite literally made of stardust. So now we've discussed the formation of the elements, let's delve into the origins of our solar system. To fully appreciate its origins, we need to journey back to the early universe, almost 14 billion years ago. Those first stars were massive compared to our sun, burning hotter and brighter. And these gigantic stars were composed mostly of hydrogen and a little bit of helium, the only elements abundant in the early cosmos. And as I mentioned earlier, they lived fast and died young, exploding as supernovae after brief but brilliant lifetimes. And these supernovae were cosmic alchemists, forging heavier elements like the carbon, oxygen, and iron in their final moments. In their explosive deaths, they scattered these elements into the surrounding space. And over billions of years, galaxies transformed into dynamic ecosystems, teeming with stars at every stage of life. Clouds of gas and dust, enriched by generations of stars, became the raw material for new stellar generations. Supernova shockwaves compressed nearby gas and dust, triggering the birth of new stars. Here's a composite image from the Hubble and Chandra telescopes. Cassiopeia A, a remnant of a supernova explosion. And you could see this shock wave pushing through clouds of cosmic debris, piling up material into dense regions. Here's a rendering showing the collapsing cloud of dust and gas. Under the influence of gravity, the collapsing nebula flattened into a spinning protoplanetary disk. At the central region of the cloud grew hotter and hotter. Nuclear fusion finally ignited, giving birth to our sun. Within this disk, countless tiny particles of dust and gas and ice collided and stuck together, forming larger and larger clumps. Over millions of years, these clumps grew into planetesimals, the building blocks of the planets. Through the process of accretion and frequent violent collisions, these planetesimals eventually form the planets, moons, asteroids, and comets that make up the solar system today. The early solar system was a chaotic and violent place, with collisions playing a crucial role in shaping its final architecture. Strong solar winds composed of radiation and high-speed energetic particles swept away the gas and dust from the system. And these winds stripped the gases from the four inner rocky planets, Mercury, Venus, Earth, and Mars. In contrast, the cooler outer regions, the lighter elements form the gas giants, Jupiter, Saturn, Uranus, and Neptune. And these gas giants grew significantly larger and less dense compared to the inner planets because they were too far from the sun for the solar wind to disperse their gases. Even after the planets formed, the solar system remained a chaotic environment. The moon is thought to have formed from the dense debris ejected when a Mars-sized body named Theia collided with the Earth. Here's the moon as we see it from today, from our front yard, and this image was taken from our porch. Jupiter had a significant impact on the early solar system due to the influence of gravity. These next few slides show where the majority of icy bodies are in the solar system. This image indicates the main asteroid belt between Jupiter, which is over here, and Mars over here. And here is the asteroid belt, between Mars and Jupiter, as I've pointed out there. It's a region teeming with rocky debris that never coalesced into a planet due to Jupiter's massive gravity. Further out beyond Neptune lies the Kuiper belt, which is out here. Jupiter would be about there. And this Kuiper belt is a vast expanse filled with icy bodies and dwarf planets, including Pluto. Even more distant is the Oort cloud, a spherical shell of icy remnants surrounding the solar system. And that's way out here, beyond the orbits of the planets. Here's an example of one of those typical icy bodies. Occasionally, gravitational nudges, whether from Jupiter, passing stars, or other celestial events, send some of these frozen relics hurtling toward the inner solar system. As these bodies approach the sun, the heat causes portions of their material to vaporize, creating glowing comas and spectacular tails of gas and dust. These tails, shaped by solar wind and sunlight, can stretch for millions of kilometers across space. We've been very fortunate to see some of these spectacular comets in the past few decades. This image was taken late at night, July 2020, from Wycliffe. As you can see, the formation of our solar system has been far from serene. It's been a chaotic, dynamic, and an ongoing process, continuously shaped by gravitational forces and cosmic collisions. But the formation of our solar system is not unique. Today we can observe similar processes in distant regions of space. We have identified numerous stellar nurseries along with their nascent solar systems. Here's just one such place. The Hubble image reveals protoplanetary disks in the Orion Nebula, a stellar nursery 1,300 light years away. These are light years wide cradles of early solar system and planet formations, very similar to the environment in which our sun was born. And you don't need a powerful telescope to see these stellar nurseries. That fuzzy patch, indicated by the green arrow, is the Orion Nebula, the birthplace of new stars and solar systems. The red arrow points to Betelgeuse, the red giant star that I mentioned earlier. I captured this image of Orion Nebula from our small telescope in our front yard. With the help of advanced telescopes, astronomers have not only discovered nascent solar systems, they've also identified over 5,700 planets beyond our solar system, known as exoplanets. Here are some artists' renditions. Some of these exoplanets are located within their star's habitable zone. And with billions of planets in our galaxy, how unique is Earth? Despite the ubiquity of exoplanets, the emergence of life may be rare. Now, I know this illustration looks complicated, so I'll break it down. Here's the Earth at the optimal distance from the sun. The sun would be out here. And these boundaries indicate where that apparent habitable zone. This is the more optimal habitable zone. This is the edge of a possible habitable zone. Our planets, the outer planets beyond Earth, like there's Mars, which is at the very edge of the habitable zone, and the gas giants would be way, way out there, well beyond that zone. We're fortunate to be in the Goldilocks zone, at just the right distance from the sun, not too hot, not too cold. There's Mars. And these are some of the exoplanets. So of these 5,700 exoplanets or so, some do lie within this habitable zone of their respective stars. However, there's enormous obstacles to become a life-supporting planet. Besides being at the optimal distance from the sun, the Earth is protected by a strong magnetic field, unlike the other rocky planets. This magnetic field, known as the magnetosphere, is crucial for deflecting dangerous blasts of solar wind. The sun exhibits an 11-year cycle characterized by intense bursts of radiation known as solar flares. And these flares are often accompanied by massive eruptions of charged particles that enhance the solar wind and potentially affect Earth. We're currently in an active phase of the cycle which is why we've seen so many auroras lately. And here is the size of the Earth for a comparison to the size of a solar flare, a typical solar flare. We see these blasts of solar wind as beautiful aurora displays. This photo and the aurora photos that follow were taken from our home near Cranbrook. Auroras are usually harmless, although occasionally they can overwhelm the protective magnetosphere, resulting in widespread disruptions to power grids. In 1859, the Earth experienced the most intense geomagnetic storm in modern recorded history, called the Carrington event. It produced striking auroral displays that were reported as far south as Hawaii and caused sparks and fires in telegraph stations across the globe. If a storm like this were to occur today, it would cause widespread global disruptions. And not only would power grids fail, but so would communication systems. Electrically triggered fires would be likely. Satellites would fail. The internet would fail. Giant storms are rare, but they do happen. Despite facing cosmic, climatic, and geological calamities, Earth has been remarkably stable, allowing life to thrive. There are too many factors to mention that contribute to a planet's habitability. On other planets, even if life does gain a foothold, things can go catastrophically wrong. Take Mars, for example. If life ever developed there, it was likely extinguished long ago. Mars once had oceans. Now it's a dry, barren wasteland, a stark reminder of how precarious habitability can be. On Earth, the journey from the first primitive single-celled organisms to complex multicellular life took about 3.5 billion years. And for 80% of Earth's history, there's only been life in the sea. This chart illustrates the timeline of life on Earth. For the first 3.5 billion years, only single-cell organisms thrived. And after 3.5 billion years, single-celled organisms, multicellular organisms began to emerge. These more complex forms have existed for only a small fraction of Earth's history, roughly 1/10 of its total age. This creature here, by the way, is one of the Burgess Shale ones from 510 million years ago, Opabina. So to put it in perspective, from simple life, it took another 500 million years and 5 major extinction events to get to us. Ironically, we would not be here had a random asteroid not wiped out the dinosaurs 66 million years ago, clearing the way for mammals to diversify and leading eventually to us. But here we are, 4 billion years after life first appeared on Earth, an intelligent, curious organism able to contemplate the universe and its own creation. We are, in essence, the universe pondering itself. But the questions remain. Are we alone? The probability of sentient life may be incredibly low. However, there are billions of planets out there in our galaxy. And there are about 2 trillion galaxies in the observable universe. How long do advanced beings exist before they too go extinct? Humanity has only been here for a fleeting moment in geological time. Catastrophes, whether born of domestic instability or cosmic events, can snuff out advanced societies. I think it's likely that other civilizations do exist out there. However, the immense distances and vast stretches of time between us mean that our paths may never cross. It is our hope that this talk has given you pause for thought, to take a moment to look up at the night sky and marvel at our vast place in this universe. Thank you.